Welcome to our celebration of the 10th anniversary of the detection of gravitational waves. Woo! Good. Which was 10 years ago exactly from yesterday. So we didn't want to make you come on a Sunday, so here we are. If you don't know me, my name is Max Easy. I'm an associate research scientist here at CCA and an assistant professor of astronomy at Columbia. I began my work in LIGO a long time ago in 2012 as an undergraduate research summer intern. And then I joined Caltech as a grad student in 2014. So my timing was really perfect because it hadn't even been a year that I started grad school at Caltech that LIGO detected the first gravitational waves, GW 150914. And these, as if you're here, you must know, this was a signal that came to us from the spiral merger and ring down of two black holes coming together and merging into a final object that settles down. And this really was a milestone in the field, not just in physics, fundamental physics, because we're seeing dynamical spacetime really directly for the first time, but also in inaugurating a new field of gravitational wave astronomy. So studying the universe, not just through light or other messengers, but through gravity. And of course, people had been working on this for many years. I like to think that I contributed by joining LIGO that 1 year, but the reality is that people had been striving for this for decades. In fact, as a personal anecdote, I had planned on deferring my acceptance of the Caltech offer. I was going to go somewhere else for a little bit. And my advisor at Caltech, Alan Weinstein, was emphatic that I should join that year because LIGO was certain to detect gravitational waves that 1 year, and I would miss out on the discovery. And lo and behold, he was right. And it was only way later that I found out that Alan had been saying we would detect gravitational waves that year, every year, for several years. But that just goes to show all the work that all those many people, Alan and many, many others, put into making that vision possible. Of course, primarily our founders, Ray Weiss, Barry Barish, Kip Thorne, who received the Nobel Prize in 2017. They really had the vision and the grit. Oh, and Ron Drever also, who passed away sadly before the Nobel Prize was given. I did want to, you all know these people, I imagine, but I did want to bring them up because Ray did pass away very recently. And so, we can never acknowledge people too much, including others like Ron Drever. And Ray's loss was a huge loss for the whole field and science in general. But of course, it's not just three people that make up a field. The LIGO, the gravitational waves as a field it's composed of thousands of people, up to 1,000 who are members of the LIGO Virgo Kagra collaboration that help run these instruments and analyze the data that they record. Virgo and Kagra being the Italian and Japanese counterparts of the LIGO detectors in the US, and we all work together to try to operate and interpret and do science with this data. Of course, this group of people and the extended gravitational wave community have been hard at work for the last 10 years. And so we have the pleasure this week of celebrating this with the announcement of a new detection, GW 250114, actually last Wednesday, which came from a remarkably similar system to that first gravitational wave detection, 150914, two black holes of roughly 33 times the mass of the sun coming together, merging, and forming a remnant of around 62 times the mass of the sun, or so. And this time, even though the signal itself is intrinsically quite similar to the one we saw 10 years ago, the detectors are not. The detectors, our technology, our analysis, but primarily the instruments, have improved significantly by a factor of 3 to 4, so that the same type of signal we can record so much more clearly. You can see all stages of this merger process even by eye. The resemblance between 150914 and 250114 is striking to the point that when I circulated this plot internally to our LIGO colleagues, someone freaked out because they thought I had accidentally plotted the old data. But it's not the same data, it's just very similar. And you can see the similarity and the striking improvement in the instruments by eye if you compare that signal from 10 years ago and what we have now with 250114 today. And so, scientifically, what this means is that we have a more detailed view of every single part of this process than we ever had before. And so I think primarily one of the main takeaways from this detection, besides the fact that the instruments have come so far, lies in this aspect that we can isolate the different portions of this process and learn something individually from the different stages, just because we have so much clarity in the recording of these data. Primarily, I would like to emphasize that we can zoom in to this final portion of this process and look at the signal that comes to us directly from the remnant black hole that was formed in this collision. And we can clearly see the oscillations in terms of quasi-normal modes of this object as it's settling down into final remnant black hole. And this really allows us, this clarity, this high definition of the data allows us to tease out very clearly and compellingly two modes of oscillations, two tones in this part of the signal that tell us something about the structure of the spacetime as it's settling down. And it allows us to verify that the remnant is indeed a Kerr black hole to much greater clarity than ever before. I think for me personally, this is quite striking because it really represents a realization of a research program that goes by the name of black hole spectroscopy or black hole seismology in analogy to astroseismology, which is trying to study black holes from the reverberations of the spacetime as they get imprinted in the gravitational waves. And so this clear detection of these two tones in this ring down are striking on their own, but also we can study them in the context of the signal as a whole. And you can do things like, we have so much signal that we can take the luxury of ignoring the loudest part of the signal and study the initial part, the final part, and make sure that the initial and final states are consistent with Einstein's predictions of what this process should be. And it really, by now, we're used to seeing these signals, but it should be striking the level of agreement in terms of the predictions for these signals between the data and the theory that you can see by eye in that previous plot that I showed you. Of course, 250114 is just the latest announcement in a number of gravitational wave signals that we have seen since 150914. We are at around 300 signals at this point that have been detected. You can see them represented here by a dot. The size of the dot is proportional to the total mass of the two black holes that merged, or black hole and neutron stars that merged in the system. The x-axis is time, and so you see the initial detections here on the left. You see 150914 and a couple other binary black holes. The y-axis is the distance at which these objects merged. And as the detectors have improved, it's not only that we see the signals more clearly, but our range also increases, and therefore we see way more of these events. All the way up to today, the instruments are currently observing, and we have a number of detection candidates that you see in those circles without those empty circles represent candidates we haven't vetted or released yet. And you see 250114 as that yellow dot, the most clearly recorded signal yet that we just announced. So today, this is an excuse to celebrate the progress over the last 10 years and to just celebrate this field in general, discuss what we have learned and what we expect to learn, hopefully over another many decades of gravitational waves. And so we have prepared for you a panel involving not just myself, but also Will Farr, Savik Ford, Yuri Levin, Barry McKernan, Brian Metzger. And we will discuss the lessons learned and eventually take your questions. Before we do that, however, Will is going to give us an overview, so a retrospective review of the last 10 years and the main takeaways to set us up. And so with that, I will stop speaking and let Will take it away, if Will is online.
I'm online. I've been listening to you, Max.
Good. Thank you, Will.
Good. Let me get my screen share set up here. Hopefully you are now seeing slides. Good. Um, yeah, obviously, there's way more in 10 years of gravitational wave astronomy than I can cover, but I'm going to try over the next, say, 10 minutes or so to give an impression of what has happened and how our catalogs have grown and what we might have learned and what might still be major puzzles in this field, just kind of trying to tee up the panel. Um, Max already talked about working inside a large collaboration, but I want to emphasize, our group here at CCA and also at Stony Brook is members of the LIGO Scientific Collaboration. There's our little logo right there in the middle, Stony Brook and Flatiron. We play a role, but it's a big group. These are some of the logos for all the universities involved, and you can see they come from England, Korea, Australia, the United States. So this is truly a global international effort. Would not be possible if we didn't have such a large group of people all working on their various pieces of the puzzle. Okay, this is really quickly sort of how the interferometers, the observatories, work. This is a schematic picture taken from the very first paper about the first detection. You can click the link down here and find it. If you didn't take a snap of the QR code at the beginning, I'll show it at the end, but that'll take you to these slides. You're sort of forced to do that because for a very long time, LIGO papers, which all have their authors in alphabetical order, are Abbott et al. So there's no hope for you to understand which Abbott et al. I'm talking about unless I just provide links. But this is the paper describing the first detection, GW 150914, and it's laying out how our interferometers work. They have a laser source. It is presently more like 100 watts, but at the time it was a 20-watt laser, and it is sent into a large cavity, inside of which is a beam splitter, a smaller cavity, which is bounded at two ends by mirrors, one of which is allowed to swing in response to gravitational waves. And this inner cavity had at the time 100 kilowatts, now close to 10 times that power, circulating in it. And as a gravitational wave passes through, these test masses swing. Actually, that's a lie. They don't swing. We control them so that they don't swing. We measure the control force we have to apply, but never mind. The test masses swing in response to a gravitational wave. The number of cycles that fit into these two arm cavities changes relative to each other. The interferometer then changes its output here into a photodetector. And at the time of the first detection, if you just left the interferometer running, and most of the time, of course, it's not recording a gravitational wave. There's no large amplitude signal inside of it. This is what the noise spectrum of the interferometer looks like. Today, this would be a factor of about 3 or a little bit more lower. But its condition at the first detection is sufficient to illustrate my point, which is on the x-axis here is frequency in hertz. So 100 hertz is not too different from the tones you are presently hearing out of my voice. 250 hertz is right about middle C, a nice treble instrument. So this is very much in the audio band. And the minimum noise, the peak sensitivity of the interferometer is just about at 200 hertz. And if you ask, what is the gravitational wave source that would produce 200 hertz gravitational waves? Those are the frequencies of gravitational waves that are emitted essentially at merger for a pair of 10 solar mass black holes. So the nature of this instrument is that it likes to detect the gravitational waves close to the merger of stellar mass compact objects. Now, if we move on the y-axis and we look at the amplitude, the gravitational wave signal that we measure is a fractional signal, a fractional stretching. So these 4-kilometer long arms extend themselves by a part or a few parts in 10 to the minus 20 or so. You can do the math, but that's a very small distance. The absolute extension is a fraction of an atomic nucleus. If you look at the amplitude sensitivity and you imagine that near a compact object merger, the space-time is distorted by some order 1 factor. As that distortion propagates in a gravitational wave, its amplitude falls off like 1 over r, just like electromagnetic waves. And so you will detect a source with an amplitude of 10 to the minus 23 when you are about 10 to the 23 of its characteristic size away. The characteristic size here is the Schwarzschild radius of the compact object that's making the gravitational waves. And again, if you put in numbers, a 10 solar mass object has a Schwarzschild radius that is about 10 to the minus 23 of a gigaparsec. So in other words, this strain amplitude will be achieved from sources that are tens of solar masses at gigaparsec distances. And that's exactly what we saw. GW 150914 was 30 solar mass black holes at a few hundred megaparsecs. Max has already shown you the wiggles, but it's striking even for this first detection how much of the signal is visible in these top panels, which are minimally processed data from the interferometers, right? You can see a good 5 or 6 cycles. Of course, in the event that occurred in January, we can see much more than that because the noise amplitude is down by about a factor of 4. Over 0.15 seconds or so, the source enters the interferometer where we first start to see it at about 30 hertz and chirps its way, increasing in frequency and amplitude up to a merger at about 250 hertz, again, in a time period of about 150 milliseconds. So this is quite short. These are bursty events, sort of extreme transients. So GW 150914 was the one that started it all literally a decade and 1 day ago. Other exciting firsts came fairly soon thereafter. Just about 2 years later, we recorded the first merger of a neutron star and another neutron star, GW 170817. Here it is, starting at low frequencies and rising now much more slowly and producing a gamma ray burst. So neutron stars are about 10 times lighter than black holes. Correspondingly, the rate at which they inspiral is considerably slower. And so this signal rises from appearing in the interferometer at tens of hertz over a period of about a minute, producing its merger. And about 2 seconds later, here on this top plot is the Fermi satellite recording a burst of gamma rays from the same source. So GW 170817 produced GRB 170817A. And we now think, I think Brian is going to spend some time on this later in the panel, that this is an important source of chemical enrichment for elements beyond iron in the universe. Additionally, I mentioned before, we have a pretty good idea of our gravitational wave strain amplitudes. We can work them out in terms of the size of the source, the Schwarzschild radius, and the distance. We also electromagnetically can observe the host galaxy of this event and therefore thereby measure distances and redshifts. And so this was the dawn of gravitational wave cosmology. This event provided still almost all of the information that we have from gravitational waves about cosmology. This plot on the right shows the Hubble constant, the expansion rate of the universe, from a paper that appeared just a couple weeks ago on Archive. And our inference from this event alone, measuring redshifts electromagnetically from the host galaxy and distances from the gravitational waves, is encoded in this yellow curve here, the bright siren. And confirms, surprise, surprise, that the Hubble constant is 70 kilometers per second per megaparsec. These vertical bands show the best result running from the CMB, from the Planck satellite, and from supernova calibrated with the Cepheid distance scale, as we heard about last week in the Big Apple colloquium. Those results are quite discrepant with each other. The error bars are very small, and the centers are 5 or 6 sigma apart. We are not yet informative about that with gravitational waves, but we hope to be one day by collecting enough neutron star mergers like this. GW 150914 and 170817 made up 20% of the first gravitational wave transient catalog, GWTC1. There were a total of 10 objects in this catalog. Here they are shown in luminosity distance and chirp mass, which is a total mass-like parameter that is measured well in gravitational waves. And on the right-hand side of the figure, in primary mass and secondary mass of the compact object. Down here is the neutron star. Here are the black holes. This was the first catalog, but already a number of things that are going to be features of later catalogs are apparent. LIGO is capable of detecting mergers well above 60 solar masses, but there were none. All of the first black hole mergers came in with masses really actually probably below 45 solar masses. And so a persistent puzzle in this field has been, why do we not have high mass black hole mergers? We think we may understand that, but it's still not fully clear what the astrophysics is that limits the upper limit of the black hole masses. Additionally, it's clear from this catalog already that the black hole mergers are going to dominate the neutron star mergers in the catalog. There's a lot of these and there's none of those. In fact, the absolute merger rate of the two sources is pretty similar, within about an order of magnitude, but the black holes dominate our catalog because they're so much more massive, we can see them so much further. Additionally, it looks like there may be a dearth of mergers here at low mass. That's a feature that I'll go into talking about our second catalog. So GWTC2, which appeared in 2020, comprised the first half of our third observing run, so about 6 months of detector time. And already you can see, just blinking between the two plots, there's a comparable amount of wall time in GWTC1 and GWTC2. However, the detectors are getting better at an incredibly rapid clip. GWTC2 has some 40 sources or so, 4 times the size of GWTC1. And in this catalog, we completed the combinatorial matching. We had another binary neutron star merger. So we've seen neutron stars merge with neutron stars twice at this point. We have a large number of black hole mergers. And we saw our first neutron star black hole merger. This GW 190426 event had a 7 or 8 solar mass black hole merging with a 1.4 to 1.6 solar mass neutron star. As before, most of the black hole mergers are consistent with being equal mass, but for the first time, we have a source here at mass ratio different than 1, GW 190412, which tells us that black holes do not always pair with a partner who is exactly like them. Additionally, there seems to be an excess of sources here at total mass 70. For equal masses, that's component mass 35. And a dearth of sources above total masses of, say, 100. But we have a notable exception, GW 190521, whose total mass is about 150, clearly above the 100 solar mass cutoff. So the puzzle deepens here. Why are black holes not merging above 45 or 50 solar masses? Well, they are, just rarely. Our third transient catalog appeared in 2021, had another 50 sources or so to add to GWTC2, another neutron star black hole system, in fact, a couple of neutron star black hole systems, also objects that seem to straddle this secondary, this gap, straddle this threshold where the secondary mass is 3 solar masses, which is more massive than we think the most massive neutron star can be, and came with a whole bunch more black hole signals, again, piling up near the 35 solar mass peak, and a large number as well in the sort of total mass 20 to 30 range. Last week, we dropped GWTC4. It's so big, it doesn't even fit on one slide anymore. These are almost 80 plus sources for which we have estimates of mass ratio, spin. spin component in the plane, precession, and distance. And we continue to see more and more features of the black hole population, including yet more sources that seem to be piling up here at primary mass 35. Some sources that are unusual. GW 230529 has a black hole of about 4 solar masses with an object, a neutron star of maybe 1.6. That's the lightest neutron star black hole pairing that we have. Yet more sources that are confidently unequal mass. Other sources, GW 231123, which was a special event paper that was released over the summer, whose total mass is something like 250 solar masses. We are learning that the spins of these black holes, this y-axis in this plot is a parameter called the effective spin, which is a projection of the two black holes' spin vectors weighted by mass onto the orbital plane. So chi effective of 1 means black hole spins perfectly aligned with the orbit straight up. Chi effective of -1 means black hole spins perfectly anti-aligned with the orbit straight down. Chi effective of 0 means spins not aligned with the orbit, either no spin or spins in the orbital plane. And you can see that almost all of our mergers have small chi effective. In fact, we believe that most of our mergers, notably not all, have very small spins intrinsically. But we see some systems, particularly high mass systems like GW 231123, that have a fair amount of spin and much of it in the plane of the orbit, causing the orbit to wobble as the merger proceeds. All of these, this is features of the population. None of the features of the population that I have mentioned have a fully satisfactory explanation. So in the last 10 years, the observations have raced ahead. Theoretical modeling, I would say, has not completely caught up. We have a bunch of puzzles now about how these compact object binaries form and merge, and that's going to keep the field engaged over the coming decade and hopefully longer. To give you some highlights of the population, and then I'll stop talking and let the panel speak. On the left is a plot from our most recent population paper released a couple weeks ago, and it shows using a method that was actually developed by Dan Foreman-Mackey in the context of exoplanets, but applied here. Bins in mass space, focus on this lower corner, primary mass, secondary mass, and the merger rate in each bin, smoothed slightly, is shown on this plot. So the overall peak of the merger rate is down here in the neutron star sort of 1.5, 1.5 bin. But it is competitive with the merger rate in the 10 solar mass, 10 solar mass, really 9 solar mass, 9 solar mass bin here, which is the peak of the black hole merging population. Here at 30, 30, you see another peak in the black hole merger rate. That's the sources that dominate our catalog, 35, 35 or so mergers. And that appears to be in both the M1 here and M2 populations. There is a peak here in the sort of black hole neutron star space. Black holes of tens of solar masses and neutron stars are very light black holes here at 2 to 3 solar masses. We now have enough sources that we think there's a preference for equal mass mergers, but not perfectly equal mass mergers. Actually, the preferred merger is something like maybe 0.7 mass ratio. So an object of 20 and an object of 15 or so merging is the favored configuration. But mergers exist across a wide range of mass ratios in our population. If we look at the black hole mass function, it has a number of obvious peaks and dips. Starting here at low masses, the merger rate at 5 solar masses is quite low, although not 0. It rises to a global maximum at about 10 solar masses and then falls steeply. There's a sharp identifiable peak around 10 solar masses. It may wobble or stay flat from sort of 15 to 30, and then there is another broader peak of mergers here in the sort of 30 to 35 or 37 before a drop by about an order of magnitude, with a long tail out to high masses of 80, 90, or even 100 plus solar masses. Each of these individual features is presumably a clue to the formation of these objects. But again, I'll emphasize there is no fully satisfactory theoretical explanation for all of the features in any one of these subpopulations. So it's an exciting time. We now have triple digit numbers of sources. And in the course of 10 years, we've seen all of this structure emerge from the gravitational wave source population, which needs explanation. Modeling is progressing, and people are very interested in that at CCA and elsewhere. And so we've come a long way. If you want to follow along, you can. At gracedb.ligo.org, we announce our detections, often within seconds of discovering them. So for example, the most recent detection, unless something's happened while I've been talking, happened September 12th, just a few days ago. And every few days, we have a binary black hole merger. The detection of these has become routine. If you have a telescope and you want to point it somewhere, we will give you a sky map. We'll estimate the distance for you. We'll even give you some estimate of the masses of the object, though not terribly precise. And so if you're into that, follow along, watch the field develop. I will say, I'm just going to leave you, I won't read it, with this quote from Chandrasekhar about the remarkable properties of black holes described by the Kerr solution. And Chandrasekhar was excited to realize abstractly that this Kerr metric in general relativity describes astrophysical black holes, but we are now seeing that directly. It's an exciting time to be in gravitational wave astronomy. The last decade has been wild. I'm sure the next decade will be even more wild. And with that, I'll conclude and let us go to our panel.
Amazing. Thank you, Will. If we can switch to the slides in the room. Now I would like to invite our panel members to come on stage. We have, well, Will Farr will be sticking around remotely. We have Savik Ford and Barry McKernan, who are professors of astronomy at CUNY, research associates at AMNH, and guest researchers at CCA. We have Brian Metzger, professor of physics at Columbia, senior research scientist at CCA, and Yuri Levin, also professor of physics at Columbia and visitor scholar at CCA. Brian, I will ask you to move because unless you want to drive the Zoom thing. Okay, let me see. Okay, good. And all right. Ah, okay. Oh, Will can't see us. We can see him. All right, awesome. So I told you we would start with him, but I think before we dive into the science, let me preempt that a little bit and warm up with anecdotes maybe that you guys want to share. I got to share my own anecdote about 150914. You know, this last 10 years has been important professionally for many of us, but also personally. So I don't know if any of you have any anecdotes about what gravitational waves and these discoveries have meant to you. Maybe, Savik, I'm going to tee you up.
Okay, folks can hear me? Okay. So some of you will probably have heard this story before, but I think it's really, I think it sets the stage very nicely, and I know that, you know, I'm sure that Yuri will actually have some similar things to say. I think that for a long time, the gravitational wave detection prospect was seen as this sort of physics curiosity, and it wasn't really thought of as important for astrophysics. And there was not a lot of, shall we say, faith that it was actually going to happen, to the extent that in January of 2016, so you may have noticed, right, the detection happened in September of 2015, but the announcement didn't happen to the public until February of 2016. So in January of 2016, there was a AAS meeting, and I had been sort of running around trying to provoke any information out of any gravitational wave people that I could. Yuri, in fact, we had dinner after a Big Apple colloquium in December, and he was absolutely impeccably quiet. Did not leak a thing. One of the few people who did not. But a lot of people had heard that LIGO had something. And as I went around to the gravitational waves people I knew, I tried to get some, provoke anybody. And I had heard recently that Paul Hertz, who was then the head of NASA's science mission directorate, had since September been heard to say, oh, I don't know why we're spending any money on those gravitational wave people. They're never going to see anything. When people kind of had hints that they did know something. So at that meeting, I was not in LIGO. I didn't know anything. I had tried to get some people to tell me things, and for the most part, people were very quiet until I went to a session, and I sat down, and it's been 10 years, so I'll name the guilty parties. Tuck Stebbins sat down behind me, and if you hear that name and you picture sort of this avuncular Texan older gentleman, that is the right picture for Tuck. I knew him like a little bit, but not a lot. And it was one of these parallel sessions at the AAS, and Tuck just sort of plopped himself down behind me, and he leaned into me and he said, "Are you inside LIGO?" And I said, "No." And he said, "Me neither." And this is very weird, all right? And he said, are you on the LIGO External Steering Committee? And I said, "No." And he said, "Me neither." And then he said, "So do you know what the LIGO External Steering Committee was just told?" And I said, "No." And the chair is now looking at us because we are making noise while people are giving presentations. And he says, "Me neither." And then he says, "But LIGO detected a 29 solar mass black hole going into a 36 solar mass black hole." And I said, "Oh my God," but I couldn't do anything because I actually had to give a talk in the session. It's one of these 5-minute things. But the very funny thing is that Barry, who's obviously my collaborator, and as many of you may know, also my husband, he wasn't able to go to this meeting because he had got called for jury duty. So he was at home in New York on jury duty. And so as soon as the session ended, I ran out and I called him up and I said, "Barry, you're not going to believe what Tuck Stebbins just told me." And he said, "Oh, LIGO detected a 29 solar mass black hole going into a 36 solar mass black hole." And I said, "How did you know that?" And he said, "Oh, Matt told me." O'Dowd. "Luis, how did Matt know?" "Oh, Luis told him." "How did Luis know?" Luis Sankordoki. "Oh, he went to grad school with a guy." So basically, it was a very, very, very poorly kept secret.
For those of you that believe in conspiracy theories, now you know why they're impossible. Like, we can't keep a secret no matter even how hard we try.
Yeah, they tried really hard, and it did not happen.
And maybe for context, we should say that this was remarkable to the community at the time, not just because it was the first detection of gravitational waves, but also because they were black holes. Many people were expecting neutron stars, and also the mass range of the black holes perhaps wasn't as obvious. I guess Barry wants to speak to that.
Yeah, I was just going to say, I think for the folks who weren't around at the time, I think our expectation was that the things that we knew were that black holes, stellar mass black holes, were 5 to 15 solar masses, because that's what we saw in the Milky Way. And so this event was immediately, the black holes involved were twice as massive as anything that anyone was typically expecting. And so this was a shock to a lot of people. There was a sociologist in LIGO, maybe Yuri knows about this and can tell us more, who was trying to work with the collaboration on the discovery of gravitational waves. And they were expecting that this would be a really hard-fought process, where the discovery of gravitational waves would be a subtle thing, trying to tease out, trying to convince people that indeed gravitational waves had been detected. And then the signal arrives, and the sociologist just throws up their hands in disgust and goes, "It's obvious, right? Everyone will recognize this, right?"
He wrote 2 books, I think, on us as subjects of his study. So, awesome. Well, thank you for getting us started. I think now we can pivot a bit more into the science. But before we get to the observational science, I do want to dwell on the instrument a little bit. And I think out of all of us here, Yuri is the person closest to the instrument who has contributed to the progress we have seen, even through theoretical work or related work. So Yuri, do you want to say what do you find most striking about this instrument and what you have seen in the last 10 years, I guess, in terms of improvements and what makes it possible?
You guys hear me?
There you go.
Yeah, I don't know. It's a little difficult for me to find the right pitch to discuss this. I came to Caltech as a theorist. I knew I wanted to do theoretical physics, but also I knew that I didn't want to do particle physics. So in the end, I ended up doing theoretical calculations of LIGO noise, of thermal noise, and quantum noise. And I don't know, am I allowed to show slides?
Yeah.
I prepared a few slides. So there was one of my supervisors was Kip Thorne, but another supervisor informally was Vladimir Braginsky, who was visiting from Moscow, and he was smoking always. I mean, otherwise he would go on smoking breaks. So this is like a picture of him. And because Americans are afraid of cigarette smoke, I was the only one who would, keep him company during these breaks, because I'm not afraid of cigarette smoke. And so I did part of my thesis on trying to come up with techniques for beating the quantum limit. Now, the quantum limit appeared first in Braginsky's paper in 1967, where it's a remarkable paper. It doesn't just discuss the standard quantum limit, which is now an absolute sort of benchmark in quantum optics and quantum science in general, but it's also discussed the thermal noise, which is also one of the main sort of sources of noise in LIGO. And Kip Thorne, he had a program at Caltech where he would, so most of the kids who would come to work with Kip, they wanted to work on relativity. And he would say, fine, but you also have to think about experiments and do calculations about experiments. And so Carlton Caves was one of those students that came wanting to do relativity. And instead, he ended up thinking about quantum measurements and came up with the idea of using squeezed light inside interferometer to increase the precision of the measurements. And so this is the first description of how squeezed light can be used for quantum metrology, written in the 1980s. So then he went on and did his whole career on quantum information theory. He's a famous professor in New Mexico. Bill Unruh, some of you may know this name, very famous relativist, but he gave a little bit of a thought to this problem as well. And Unruh realized in an absolutely groundbreaking paper, which wasn't even published as a paper, but was published as a proceedings in a certain conference, he realized that you can actually beat Braginsky's standard quantum limit if you used a particular type of squeezed light. So you have to use a squeezed light which has a correlation between the amplitude uncertainty and the phase uncertainty. So it's kind of skewed squeezed light. And he wrote this in a proceeding, and people kind of forgot about this for 20 years or so. And then I guess the next stage was when Kip became worried that we didn't have the right techniques for beating the quantum limit practically in LIGO. And the problem with Unruh's method was that it was narrow band. It would only operate within the narrow band of frequencies. So Kip organized a series of seminars or reading group, and all of Caltech's experts in quantum theory, John Preskill, Jeff Kimball, quantum optics people, just sort of random people also would come into this and listen. And so out of this seminar meetings came this idea, which is actually due to Jeff Kimball, here shown on the left side, famous quantum optics person who was the participant of this group, of how to turn Unruh's narrowband scheme into a broadband scheme. And so he realized that if you use the so-called input optical filters in a certain configuration, you could achieve this. And so we wrote a paper about this in 2001, so to speak. And then, can I go to the next slide? At about 2 years ago, I get a letter together with Jeff Kip and Sergei Vechenin. For some reason, he left Andrei Matsko out. We got a letter from Rana Adhikari saying that they have a preliminary result implementing these filters in Livingstone and LIGO. And the attached was a graph which showed very convincingly the broadband measurement below the standard quantum limit, which was absolutely amazing. And Kimball responded. So Kimball, this was January 2023. This was basically 1 year before he died. He was already not well, as you can see from this email that he wrote. But so he was retired from Caltech. He was in Texas, in Austin. And he wrote, I'm going to come to Caltech in person, and you're going to tell me. You're going to brief me on all the measurements. And so this is in the email here that you can read yourself. He gives his schedule. He says he can't actually come himself. His wife, who is his caregiver, has to travel with him. So I wrote an email yesterday to Rana. I said, Rana, did he ever come? And he said, oh, yes, he came. And we had the full scientific discussion, the full briefing. So he came just because he was interested. He was emotionally invested in it. And I think this is something that our generation has to learn from the previous generation, and we have to keep this, pure interest in science. The guy was a few months before his death. He was still interested to learn about the impact of the ideas that that he developed 20 years ago. Okay, and just the last plot is the actual measurement. You see, this is like a fantastic achievement that LIGO now operates. LIGO now beats Braginsky's standard quantum limit in quite a broad band. So if you see this purple curve, these are the measurements of the optical noise, and this kind of reddish hyphenated line, you can see that between 40 and 70 hertz, at least in this particular measurement, the standard quantum limit is beaten by this non-trivial squeezing. And you can see on the left side, you can see the scheme of how you operate. You can see the filter cavities, which are actually quite a bit modified from the ones that we were calculating over 20 years ago. They're much more handleable, shorter, only 300 meters as opposed to 4 kilometers. But anyways, this is a fantastic achievement. You need to think about the Heisenberg uncertainty principle for 40 kilogram test masses which are hanging. And the Heisenberg uncertainty principle imposes quantum limit, and we are beating it. This is amazing. This is like, I think, looking back, our descendants will be proud that this is something that we managed to achieve.
Yeah, absolutely amazing. Thank you for the story. I think when I start to explain to people how our field is exciting, this is one of the things I highlight, that to study these cosmic, cataclysmic events, you have to understand matter at the tiniest of scales and deal with quantum processes that seem totally removed from the things we're trying to study. And this really brings this home. In terms of the excitement, I think about the science, Ray was another person that was like that, and was at MIT even till last year, I think, very daily working on the instrument. So thank you, Yuri, for giving us a perspective of the instrument and what it has taken to bring us here and hopefully move us forward. I think at this point we can maybe pivot a bit to the observational side. And so I would like to ask you all, maybe to reflect on the impact that these gravitational wave instruments and their detections have had on your specific subfield over the last 10 years, if there's been any particular surprises or big, I guess, unexpected results. And maybe let's start with Brian, if you don't mind.
Thanks. Yeah. It takes a bit of a faith. So I started working on the counterparts of neutron star mergers basically when I was starting as a postdoc at Princeton. But I didn't start in that area. I started in actually nuclear astrophysics. I was trying to understand where the heavy elements were produced. And I was also very interested in the origin of gamma ray bursts. So these are observational. In fact, most of what I do, I'm very, very driven by what we see and trying to explain it. And so it takes a bit of a leap of faith at that time to put a lot of your career into something that, as was already mentioned, was considered kind of speculative. But there are many reasons to think about, specifically working on the electromagnetic counterparts of mergers. And I think, in fact, I wouldn't say I mostly got encouragement during this time. I was also told by certain people along the way, oh, you're wasting your time. This is never going to happen. Or why are you working on this niche area of nuclear astrophysics? Because we were really trying to understand where these heaviest elements come from. It seemed like the dominant model, supernova, wasn't working. And I was also just like, how are we going to actually test this? How are we actually going to have evidence that when we see these heavy elements created? And we had that opportunity with 17817, amazing event. We had done work to try to predict what would be the signal if you eject neutron-rich material from a merger, what would it produce in terms of optical radiation? And I would say we got remarkably close. This upper left-hand panel was basically from a paper that I co-authored and led in 2010, where we sort of made the first, I would say, quantitative predictions of what these counterparts would look like, where you have radioactive decay of the material during the merger. And if you actually just took our figure 1 and overlaid the kilonova that was seen after 17817, it matched remarkably well. And this was a bit of a coincidence because, of course, we had to assume something about how much mass was ejected, and there's some uncertainties here. But sort of what drives you is that, what drove me in this is I think I'm interested in working on simple problems, not hard ones, or things that I think are robust. And so what we found is, neutron stars merge, neutron-rich matter is ejected into space. It's very difficult for it not to become radioactive. And it turned out, you'd think, oh, that's got to be super dependent on all the nuclear physics uncertainties. But what we found was surprising was that actually helps you. The statistical ensemble of decaying nuclei that powers this light curve, that statistics actually helps you in making a fairly robust prediction. And so we found that these events were, 1,000 times brighter than a nova at peak. And so we gave them this name, kilonova, in that 2010 paper, and that stuck. I'd say one of the really, to me, exciting things was the way that this discovery brought together different fields that were talking to each other to some extent, but I think this event really brought them together. The community of people who were measuring the properties of these nuclei, as I said, this was sort of a niche field thinking about these elements, and then bringing together the gravitational wave and astro community, the kind of coordination that was required to be able to have the telescopes ready to quickly point and discover this event. And so I think, to me, just seeing how that has gone from a field where I would go to separately these different meetings to where now we frequently get together and talk about science. So that was, very exciting. And as Will said earlier, it's just really amazing, this merger, how many things, sort of firsts that came from it. That we had this long suspicion going back to Baczynski and Eichler and Jim Latimer, that there was a connection between these mergers and gamma ray bursts, and that was confirmed, even though the properties of this gamma ray burst were rather weird. The fact that, we learned something about the equation of state of neutron stars from both the tidal deformability, but also the outcomes of these mergers. As I said, this was the first time we had no clue where these heavy elements were coming from. And we don't know if mergers are the only source in the universe, but this was like, direct evidence of that. And then, the fact that we had this kilonova, that was key, because without the optical discovery, you wouldn't have the localization to have found the host galaxy. And so that becomes the key to using this H0 technique that Will mentioned, is these kilonova. So from something that, turned out to be a niche interest in the origin of gold, it sort of expanded to something that became very important. And so I remember we were debating a lot. I was at a meeting 2 weeks before 170817, and we had a poll at the end of the meeting, like what would be the first counterpart that we would see from the merger. A few people said gamma ray bursts. Most people at that time didn't believe that there was this thing called a blue kilonova that I'd worked on, and so they said this red kilonova. But very few of us anticipated that at the end of '02 it was coming to a conclusion that we would already detect a merger. And it turns out in retrospect we got very lucky. But anyways, it's been a very exciting event. There were a lot of, I'm not going to go through this, but there were a lot of different things we saw from this event that we sort of anticipated we would see. And there are things we didn't see or that we didn't have access to. For example, what's happening in the first few hours when these, after the merger, there's some ideas that this should give rise to very bright ultraviolet emissions. And it would be great if we can see that in the next event. Or some people have speculated that before the two neutron stars merge, there could be a burst of radio waves or X-rays or something. That would be great to see. So anyways, I'll stop there, but I'll just say there's a lot of, we'll come back maybe to the future stuff, but there's a lot going on. Yeah.
Yeah, amazing. Savik, Barry, do you have a favorite? Yeah.
Yeah, I mean, I think in terms of like the surprise, and I think it's very, especially because there's a lot of young folks here, I feel like it's very hard to convey what things were like before 1509-14 in the sense of even, and I think this might be the next slide. Oh no. Yeah, surprise. There are binary black holes that merge, right? That was not the promise that LIGO was funded on, right? It was the hope, but the thing that everybody was really pretty confident that there would be neutron star binaries that would merge. But it wasn't clear if binary black holes would actually form that so far apart that their gravitational wave decay timescales would be so long that maybe they wouldn't actually be detected. And I think, there were plenty of people who were pretty sure that that was really going to happen, but when you go to a funding board, you have to be 100% sure. And so, LIGO was sold on the neutron star binaries. And then, people were, again, and I would say this is particularly on the general astrophysics side, as Barry mentioned, right? Sort of 5 to 15 solar masses is what we'd seen in our own galaxy before LIGO turned on. So that's, of course, we're normal, right? Copernican principle, sometimes it fails, guys. And also this is maybe a different population. And then again, although the rate falls after 50 solar masses, it doesn't drop to 0. And so particularly some of these high mass mergers that we're seeing now, I think are very exciting. I guess I came at this from very AGN, sort of very bog standard astrophysicist, not necessarily super excited about gravitational waves per se, but just, oh, that's a cool tool. Oh, you guys can tell us things? Fantastic. I will take that. Sometimes. And oh, look, that presents also additional puzzles and fun things. So I think just looking at this plot here of the primary masses is, if you had showed this to somebody 11 years ago, they would have been like, you are joking. That's not right.
Well, even today.
Yeah, there's still.
Know.
Yeah, right. Sometimes you still get that. So I think, having and I guess sort of very particular to my field. So the next slide, right? If binary black holes are merging in AGN, of course, the default assumption is binary black holes merge. They're black holes in a vacuum. You're not going to see anything. But if you put them in an AGN disk, then maybe you will. We don't know if we did see one, but there was a candidate counterpart. That we were part of that. And of course with LSST and Rubin, I think that's very exciting. We'll be able to say something because at the moment, the error volumes are still pretty large for optical telescopes, and, no shade, very much appreciated everything you guys do. We love you.
Give us more money.
But, but it's a little hard to survey most of those error volumes thoroughly. But, with LSST, and with the AGN counterparts, often they're not expected to be quite so prompt or short-lived, and so you don't have to be on them in milliseconds. So that's, I guess this is sort of cool stuff that people hadn't thought about, and now we are thinking about it, and then also hopefully looking forwards as well a little bit.
Barry, do you want to add?
Yeah, so immediately after this comes this meme was the moment when I realized that the broader astrophysical community was taking the idea that binary black hole mergers might happen in AGN, for example. Maybe we were on a par with primordial black holes. It wasn't clear, but, at least we were in the picture. And so I think, certainly scientifically, I think both myself and Sav would agree that the really interesting thing for us is that LIGO is going to tell us what AGN and nuclear star clusters are like. That's the amazing thing. And I kind of didn't appreciate that back 10 years ago, but I really do appreciate it now. So thank you guys for what you've done, the miracles that you guys are doing with engineering.
Thank you, Yuri. Yuri, do you have a favorite astrophysics result, or all of it?
I have to say that I'm looking forward to other things other than
You're
binary black hole mergers, which are great and fascinating. By the way, I was a little surprised Will did not comment on the mass gap. I mean, there've been papers on the archive over the past few days about the evidence for mass gap from new LIGO data, and you haven't said anything, Will.
Will is online, hopefully.
Yep. I was trying to be quick and broad, but indeed, gaps, bumps, etc. are always a question. The mass gap that I think Yuri is referring to is this precipitous drop.
Stability,
of mergers that you can see on this slide above sort of 40 solar masses, which before LIGO turned on, there was an expectation that sufficiently massive stars blow themselves up through this process called the pair instability. You can ask Yuri about the physics afterwards if you want to, and therefore do not leave behind massive black hole remnants. So the black hole mass function would stop somewhere. And if you tried to calculate from, first principles and stellar modeling where that would be, it was about 45 solar masses, maybe. And so in the first catalogs of LIGO, when we started to see black holes maybe up to 45 solar masses and no higher, this was very exciting. Look at this, stellar astrophysics is confirmed. And then we got more extensive catalogs and started to see black holes of masses that were higher than 45 solar masses. But not so high. It turns out the pair instability stops at sufficiently high masses of stars, so you can make 120 solar mass black holes again. But there should be a gap in theory from 45 to 100 plus solar masses, and then we saw mergers in that region. And additionally, this feature that we see here, this bump at 35 solar masses, if that was at 45 solar masses, it would match the pair instability story perfectly, because there should be failed pair instabilities that leave behind remnants that pile up right at the limit. And these are called pulsational pair instability process. But the limit should be 45 solar masses, not 35. So what is that bump doing there? And so I would say over the last few years, people had, at least maybe the vibe was souring somewhat on the pair instability as being a source of this bump. And maybe something else was going on. Maybe the pair instability was operating, but we couldn't really see it in the data. And then just with this latest catalog, there is a claim, which is quite exciting, that you don't see the effects of the pair instability in the primary black hole masses, this M1 that's plotted here. That's the heavier of the two merger objects. But you do see it in the secondary, the lighter of the two objects. And that has kind of reinvigorated this discussion. And the thinking there is that the heavier of the two objects could be a black hole that's actually made out of other black holes in what we call a hierarchical merger. So it didn't come directly from stars. It's actually a merger remnant from some previous merger. And it's only the secondary black holes which come from stars and therefore are subject to the pair instability. And at least if you fit the data in a certain way, you can convince yourself that maybe that's what we are seeing. I do think that's probably one of the most exciting things to come out of our GWTC4 catalog. So I guess Yuri has teed me up nicely to answer Max's question, which is what do you think is an exciting thing that we have learned? I'm not sure I'm ready to say that we have learned that the secondaries are subject to pair instability and that's what's producing our systems, but it seems like a tantalizing hint.
Yeah, and certainly if that feature is real, we expect it to enhance with the next catalog. We're going to take questions at the end. Is that okay? Unless...
I just was going to ask a comment on the...
Do you want to turn on your mic? Otherwise, they can't hear you. Oh, well, we can.
Ask about the lower mass gap, but we can talk about that later.
That's fine.
If you want.
I was just going to amplify that. Do you have any comments on the lower mass gap? Or Max or anybody?
I think we'll...
I think it now does not seem to be a fundamental outcome of whatever compact object formation produces our black holes and neutron stars. We have one source already that clearly has a black hole that is in the sort of 4 solar mass range. And we have other sources that are close enough to that in the LIGO population, at least, there doesn't really seem to be an obvious gap between the heaviest neutron stars and the lightest black holes. That's quite different to the population of black holes that are seen in X-ray binaries in our galaxy, which I don't think is incredibly surprising necessarily, though the expectation maybe was that since in our galaxy we don't see black holes below about 5 solar masses, maybe that was something fundamental about supernova explosions and black hole formation. But it certainly doesn't seem to be the case for the LIGO systems. So if you want to explain it in the X-ray binaries, you probably need to turn to something contingent about those systems. Perhaps it's just a selection effect. The ones with low mass black holes don't turn on. Or maybe some other property of the formation of those systems.
And maybe
does that answer the question?
To draw the distinction maybe with the upper mass gap, this was a purely observational expectation, right? The lower mass gap, whereas the upper mass gap is driven by nuclear physics.
There's no convincing theory, as far as I know, behind the lower mass gap.
Right.
That's correct.
I was also going to say that in this catalog, I think the striking thing are the spins as well.
Mm-hmm.
The spins, we now know a lot more about the spins, and at least to me, as an astrophysicist, it's always interesting in the black holes that we knew before LIGO, from X-ray binaries in the galaxy. There were claims that they were actually spinning quite rapidly. I mean, mind you, these claims were based on people claiming to understand accretion disks and models of accretion disks. As I guess Barry and Savik will tell you, is not so easy, generally speaking. But the published numbers, the observers who were doing the analysis were publishing strikingly high numbers for the spins of black holes and, say, low mass X-ray binaries. And the question is, of course, if the black hole in low mass X-ray binaries does have high spin, it has to be its spin at birth. You cannot spin it up by a low mass companion because it's just not enough angular momentum in the material that companion has to donate to the black hole. So this would argue that for some reason the black holes, if you believe the observers who published these results, it would argue that the spins of black holes and low mass X-ray binaries were high from birth. Yet LIGO didn't show such high spins. In fact, most of the spins that have been measured are quite moderate. I guess we are now starting to see somewhat higher spins in some, especially of the black holes which are going into the mass gap, right? And there is an interesting connection between
with the mass and the spin.
With the mass and the spin. So, so that's something that is interesting to think about for astrophysicists.
Okay, I think if you're okay, I think we should maybe pivot to think about what you might be excited about for the next 10 years of gravitational wave astronomy. As you've heard, there are many unanswered questions. So what's on your wish list? Just answers to all these questions, or what? Yeah, right.
A huge wish list.
Of course.
So can you go back to my?
Yeah.
I'll say.
Do you want this one?
Yeah, we'll start with the boring. No, no. I mean, I think the most, as far as binary neutron star mergers, we need to see more of them, right? We've seen one, and we've had other ones, candidates at least, that where we didn't find the counterpart either mostly because maybe one detector was running and the error region was large, or was not ideally localized on the sky. But the general expectation is LIGO tells us what goes in, and electromagnetically we go out, and we have this sort of, due to numerical relativity simulations over the last decade, we have this sort of picture that depending on the mass of the binary neutron stars, they're actually very different outcomes, orders of magnitude difference in the energy released from the system. If you have a very high mass merger, the expectation is I'll make a black hole promptly, very little eject, a very dim counterpart. If I have a low mass merger, I can produce a neutron star that might have an enormous rotational energy, probably highly magnetized, and you may be able to extract a larger fraction of that neutron star's enormous rotational energy budget before it makes a black hole, if ever. And so, if we see higher mass black holes like 0425, which was one of these where we looked for a counterpart, didn't find one, big error region, hard to say what's going on, it could have been a prompt collapse case. And we're starting now to see also maybe some lower mass neutron stars, which is my next slide. But anyways, this is, I think, one terrain is like, what is the diversity here? And how does that map onto the properties of gamma ray bursts, where we actually are starting to see kilonova after gamma ray bursts, and we're seeing there's diversity in their properties. So how do we map what's going on with the GRB to what's going on? And I think gravitational waves are what is going to tell us that, because it's the precision probe of that ingoing properties that is so critical to mapping this out. Okay. Awesome. Maybe I'll let other people. I have another slide. So going down to the very speculative, crazy stuff, and I'll just say 2 seconds on this. Is, are there mergers of objects less than a solar mass? Of course, they're primordial black holes, might be in that mass range, highly speculative. I've been giving a lot of thought recently to how to make neutron stars below a solar mass, because you can't do this in ordinary core collapse supernova, because the Chandrasekhar mass of the iron core is at 1.4-ish. So no modern supernova simulation gives you a neutron star less than 1.2 solar masses. But one environment where it may be possible to do this is if you have a very rapidly spinning star that collapses, where not all the star falls into the black hole but lands in a disk, and it may be possible that this disk becomes gravitationally unstable. It requires very massive disks. It may be hard to pull off. But if this disk becomes gravitationally unstable and can cool through neutrino emission, you may get basically collapsing to form clumps that could form neutron stars with a range of masses that are no longer bounded by the Chandrasekhar mass of the iron core. And so we sort of propose this as a sort of like a small analog of the AGN black hole system. It's like this happening in a few minutes in a massive star system. And so anyways, with a student recently, we showed that this was possible. I'll simply say that this would be, I think, the only way I can think of in nature to produce binary neutron stars. This was actually first proposed by Fall and Pirro, and we sort of been developing some of the consequences of that. So the expectation here is if there are subsolar neutron stars merging, they should be accompanied by supernova, not by kilonova. And I will simply say that a few weeks ago, there was a sub-threshold LIGO event that had a chirp mass less than a solar mass. And when the observers followed it up, it did seem to have a supernova in the error region. It's subthreshold, so it's highly, take it with a grain of salt whether it's a real source. Maybe the experts here can tell me more. But anyways, there's this possibility. There's this possibility. So finding subsolar objects, I think, regardless, would be extremely exciting. I'll stop there.
Awesome.
I was just going to say on things that I'm looking forward to in the future, if we have an event like this in 10 or 20 years, I would love to have, a panel of students in the audience who are telling the audience, right, about what they've learned over the last 10 or 20 years. I'd love to learn the fraction of events that are coming from AGN, whatever that number is. So the important point is that it's a win-win. If the number is really small, that's excellent. That tells us probably that AGN disks are pretty small. The playground in which we think all of these processes are going on is pretty small. But that has consequences, right? That tells you that maybe the final parsec problem, the merger of supermassive black holes, is not solved with gas. And it maybe tells you that the feedback that we think we need from AGN maybe can't be that persistent. You can't run it that strongly. That would be a fabulous result. If you think that the fraction is maybe a bit higher, maybe that gives you slightly different conclusions. But I would love to know this answer, because right now we cannot observe AGN disks in detail. We can observe 2 nuclear star clusters, right? Or we can resolve 2 nuclear star clusters. So LIGO is going to be able, hopefully, to tell us what AGN and nuclear star clusters are actually like. And that's the thing that I'm most looking forward to.
Yuri, you wanted to add?
I just want to say that there is a road out there beyond binary mergers, and yes. In particular, even within LIGO community, people have searches, for example, for gravitational waves from spinning neutron stars, rapidly spinning neutron stars. If such waves, I mean, this is a very different signal. The evidence for the signal has to be accumulated over a long periods of time, months or even years. And it helps, for example, if this type of signal comes from known pulsars, because then you don't need a template. You actually basically already have a you have a timing model which is very precise for this pulsar. So this timing model also applies for gravitational waves. But if we see gravitational waves from one of the sources, that would mean that there are probably hidden very strong magnetic fields inside the star which don't come outside. So that would be kind of exciting. Another thing which is interesting from my perspective is signatures from the early universe. One of the most commonly discussed are bursts from cosmic strings. These are hypothetical objects. We don't know if they exist. But if they do exist, this is a complete revolution in physics. So this would be remnants of very early phase transitions and that have lived to our days, and the only way in which we can learn about these remnants is through the gravitational wave signature that they produce. So these are the 2 things that came to my mind.
Awesome. Salik?
Yeah, so I think picking up on some things that several people have said, I would be delighted if we could get the gravitational waves from a supernova in our galaxy, which obviously is not totally up to the detector people. Mm-hmm. Yeah, I think this is just like a very different way of understanding the universe. And I think, folks may know I'm fairly interested in the history of astronomy as well. And you look back and, we've been using light to gain information about our universe for millennia. And nearly everything that we know about our universe is because we have figured out how to extract the maximum amount of information from every photon that gets here. We have done okay with neutrinos and cosmic rays, but I think gravitational waves are really the real messenger that we can start to dissect, and I feel really lucky that I get to live through this and watch us figure out how we can do astrophysics with this completely new messenger that really carries the kind of information quantity I think that light has previously given us. And so, specifically looking forward 10 years is the launch date for LISA, which will definitely not slip. But, so, and of course we're already also, we've rightly celebrating the 10-year anniversary of GW 150914, but also now we have detections of gravitational wave background from pulsar timing arrays at completely other scales, still binaries. Sorry, Yuri.
Maybe.
Maybe not. Maybe not. That's true. We don't know. But so I think really we're just learning how to capitalize on this new messenger, and it's I think as the past 10 years have shown, some of what we're going to learn is the sort of things that people didn't really entirely guess at beforehand. Who would have known that LIGO was going to tell us about AGN? Like, that's actually weird.
Yeah, so that's a great point to end, I think. I mean, that's what I wanted to close with, which is the next decade we'll see a new generation of instruments if everything goes well, both in space and on Earth. And wouldn't it be great if when those turn on, we're also surprised, just like we were when we saw black holes instead of neutron stars, and perhaps even more widely surprised. Okay, so before I let you all answer questions, I'll remind you, in case you have to leave, that there will be a reception on the 12th floor following this, and you're welcome to join us. But we can take a few minutes for questions here in the room or on Zoom. So I invite you to, if you're in the room, turn on your mic by pushing the button on your armrest, and just raise your hand, I guess, for anyone, including Will. And say your name, maybe. Yeah.
Okay, my name is Kennedy Jeter, and I was just wondering, because you guys mentioned a couple times that the expectation was to see neutron star mergers instead of black hole mergers. Why was that the expectation?
We knew that neutron stars existed in binaries and were decaying via gravitational waves thanks to the Taylor-Hulse pulsar. Like, we knew for sure that those things existed, but we didn't know. We knew 0 binary black holes existed for sure before LIGO turned on, because we can't see them.
I think it's a tried and true thing that that's the most amazing thing about LIGO, is that so much was built without any detected sources. In every other area of astronomy, you detect the first source with the thing in your backyard, and then you build bigger and bigger. And that this community had such faith that in Einstein and in the fact that these pulsars. So yeah, that was their guaranteed source, and that's important to the case they made to build it.
Building on that, I'd say that there's an old model that says that the drunk looks for their keys that they dropped under the lamppost, because that's where the light is. And so astronomers are kind of very like that. We tend to look for things where we know we should see things. Right?
But of course, I've asked Kip that before, and he said he always expected black holes because they're just louder, I guess. But he trusted they formed, I guess, yeah. But they have to exist.
I mean, right? Like, there are many papers from, like, the isolated binary channel people had predicted rates and masses and all kinds of things, globular clusters as well. AGN's got a prediction that they would be there, without a lot of detail before the detection, right? Like, it's not like nobody thought that would happen, but if you went to the average astronomer was like, "What are you guys doing? You're weird." And then as soon as the detection hit, and I said this at the AAS meeting that January, I said, as soon as this becomes public, everybody's going to be like 8-year-olds with a soccer ball. Like, you can check that AAS. It's interesting if you just scroll back and you check the titles of what the sessions were before 2016 and after. There's one gravitational wave session. Literally, one, and now it's oh yeah, over here.
We have time maybe for another question. Oh. I didn't see whose hand went up, so you have to, yeah.
This is Sean Ray. Most of you know me. But one of my questions was, given when LIGO turned on, like you said, that the AGN channel was kind of unexpected in, excuse me, in being something that you'd find from LIGO. Do you think that there's like when we're kind of further improving detectors with like Cosmic Explorer, Einstein Telescope, LISA, do you think there's maybe either another channel or another source of there's like more things that like we're just not thinking of at all that when we turn it on you can kind of be like, whoa, like this wasn't expected at all. Like are there hints of that what it could possibly be, or you have no idea? Like what are your thoughts?
What are currently the current lab papers?
Yeah.
So the answer is no one knows, but we all hope that we will see new weird things that no one sort of thought of, right?
And we should say that we don't even know the channels that form the things we see for sure. So like, yeah.
Book by Martin, is it who? Not
Harwit.
Harwit, right? About
gonna
the nature of scientific discovery and generally, yeah. Whenever you open a new detector and it expands the horizon by an order of magnitude, there's always something. So it's actually a good idea, yeah, to be thinking about what anything that could be detected. How would you explain it, right? So.
I think it's first saying that for example, there is this upcoming detector, space-based detector called LISA. And people who are thinking about the sources for LISA, they're re-examining the physics of galactic nuclei, and it's becoming useful for general astrophysics even before LISA comes online. Just focusing yourself on questions which are related to gravitational wave sources can also teach us something about other things.
And I want to emphasize it's really important in astronomy I think to make predictions, because we can't go and poke the thing. And if it's your theory's worth a lot more. Like thinking back to this Killenov example, if nobody had worked on it, would people believe after the fact, if we had developed the models, that was the explanation? I'm not sure. Because then someone else might say, oh, I have a theory, and then someone else says, I have a theory, and then it becomes muddled. So I think it's really important to get ahead and to what extent possible and make predictions.
We'll take your question on Kishalais, and then we'll wrap up.
Hi, Emily McPike. Sort of a relevant follow-up. Barry and Savik, you guys were the first in this crowd of people thinking about the AGN channel. What was the sort of first thought of that production pathway to making, gravitational waves having embedded black holes in an AGN disk? Like, when was the first time as scientists you start to think about that?
Well, so the idea of things embedded in AGN disks, so the idea of AGN as a disk of gas plus a nuclear star cluster interacting with it goes way back, right? So Jerry Oestreicher I think is the first person to propose this back in the 1980s. There are various groups who worked on this in the 90s. Yuri worked on this as well in the aughts. We were lucky enough to predict that sort of LIGO should. I say lucky enough because it was a year before LIGO actually detected something that we said that LIGO should observe mass merger hierarchies coming from AGN. It should so it was very simple, quite naive, but we predicted that AGN should be excellent sources of intermediate mass black hole formation because the escape speed is so high that you're more likely to retain these things, and so this is the sort of thing you should be looking for. And so I think that certainly the roots of our thinking, probably 2011 or so, we started making analogies between protoplanetary disk embedded objects and the black holes and stars that should live in AGN disks. But the idea of things in AGN disks goes back decades, right?
Okay, I think we should, for the sake of time. Yeah, we'll take your question. No, I think just, what's that? No, we'll take your question and then we'll, oh, I'm sorry, unless it was answered already.
Wait, so this goes back to the point of, we briefly heard about the possibility of detecting nearby supernovae. And what I've wondered is that how well prepared are we even today in today's LIGO data to to actually spot an unexpectedly weird signal from a nearby supernova? Because my impression is that all of these detections are enabled by template matching, and I would not be surprised if we have no idea what the signal for a core collapse supernova looks like. So if there was a burst of something, you know, are we covering all grounds on that front to detect the unexpected?
I mean, that's right. We do have search pipelines that look for arbitrary morphologies of signals, and the way they work is by looking at cross-correlated power across a network of detectors. So you need multiple detectors to do this. Necessarily, the range of those is worse than if you already know exactly what the signal is going to look like. But we do have a few search pipelines that should be able to reach a supernova within the Milky Way, I think, 10 kiloparsecs.
Well, to drive that point home, a fraction, I think it's about 1/3, but you can check the papers to get the precise number, of our existing binary black hole mergers are also detected in burst pipelines.
Yeah.
So, you know, they function. They don't work well for picking up neutron star mergers because those are very long and you have to average over many cycles to build up the power. But particularly for high mass black hole systems, they are not as efficient, but you know, within spitting distance of the efficiency of the fully templated searches.
And the heavier black
holes. So they work in practice.
Yeah, especially for the heavier black holes, which I think.
There are also methods to search for what the LIGO people call long transients. So this, I mean, I guess it's kind of similar to bursts, but it's like, you know, bursts are typically people think are short, and long transients are bursts which are not short. I mean, these are the things which go on for seconds. For example, if you have a collapsar disk, it's not quite from the it's not quite from the modes of the neutron star itself, but it's, you know, if you form a disk like in Brian's story, you could also, in the disk itself, could be the source of gravitational waves, as Or Gottlieb worked out, actually, somebody here at Flatiron. So for this type of things, also people have pipelines, and they train pipelines on the theoretical signals produced in simulations. So they play the war games and see if these things can be detected.
And you can tune their parameters to specific morphologies, but yeah.
Wasn't 5914 seen by a burst?
Yes, it was, but it wasn't the most significant pipeline to see it. But yes, it was picked up by. I think it was first noticed by a burst pipeline. That's right, CWB. Yeah. Okay, so with that, I think there's a reception waiting for us. But first, join me in thanking all of our panelists and yourselves.